Hello, welcome to the fourth live session of Quantum Topology 2 NPTEL course. This is Shavik, third scholar of IDM investment group discussion.
Hello, sir.
So, tell me, Mustaq.
Can you hear me?
Yeah, I can hear you. Are you able to hear me properly? And I know, are
So
you able
I
to hear
have
me?
some question actually in the last class from the last class.
Mhm.
But can you please explain why real line with lower limit topology, not second countable, but is the first countable?
Real line is lower limit topology, right? Real line is lower limit topology, right?
Yeah.
Okay. Before studying, let know whether are you able to see the screen or not. Are you able to see my screen or not? Okay, I hope you are able to see the screen. One minute. Okay, so your question is why lower limit topology is first countable, not second. Okay, so R with lower limit topology. Mm, One minute. Some syncing conversation. Just hold a minute. There is some issue with software itself. I guess it is not synchronizing properly. Just hold a minute, Mr. So, hold a minute. Yes. One minute. It seems. Wait. I'll hold a minute for listening. There is some issue with software itself. Yes. Okay. So it is now software is working. Okay. Yeah. Okay. So the software is working. Let me share my screen. Sorry. What is the screen? Here is the screen. Mustak, now can you please confirm whether the screen is visible to you or not?
Yeah, I can see the board.
Okay. Okay. So your first question. Okay. So your first question was that why lower limit topology? Lower R with lower limit topology is same. Uh, Not second countable. but not first. Oh, that's a pretty good question. So, well, so, so, um, so first question is why R with lower limit topology is not safe countable. So suppose it is second count. Okay. Suppose. So for each x belongs to RL. So and so let's if it's second countable, so let capital B be countable basis for it. Okay. It's a countable basis, and there is till now I think everything is fine. So so for each x belongs to RL, there exists an basis element b beta x belongs to capital beta such that x belongs to beta x, which is subset of x comma x plus epsilon. Correct? Okay. So this implies what? This implies infimum of beta x equal to x. Correct? So this implies what? This implies that if x not equal to y, this implies beta x and the beta y, these states are not equal. So this does what? This collection beta x cannot be counted. So that is the thing. So collection betas cannot be counted. So that's why our with lower limit topology is not same count. Okay. So now I hope till now this much is clear. Now the second question is the following: that why R with lower limit topology is first count. So for first quantum, what we need to choose. So for first quantum, what I need to prove actually, if taken a point from a real line, we need to take a point from real line, and we need to choose a collection of open set around that point. So that if you take any arbitrary open set around that point, that open set will contain at least one of the elements from the countable subset of real. So for this, what we can take, so we take x belongs to RL, okay, and take the countable collection UN giving x comma x plus 1 by n, okay, in. So now if V be an open set in RL containing x, so this implies what? This implies x belongs to x comma x plus epsilon for some epsilon greater than equal to 0, and we can choose a 1 by n or so 1 by n not less than epsilon. So these implies that x belongs to x comma x plus 1 by n naught, each is subset of p. So these implies this collection even makes countable collection satisfying the desired property. So that is the thing. Okay. Are you understand the points? Are you able to understand?
Yes, yes, I can.
Oh, okay. 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 So do you have any more
I
questions?
have I have
Yeah.
another question.
Yeah. Please.
I have another question. I no, it's a only. Sorry.
Oh. Okay. No problem. Okay. That's good.
Okay. Thank you.
Okay. So today, well, okay. So today we shall first. Okay. So in last session, So in last session we have done countability axioms, separate axioms, all those things. Sorry, we last semester we have done actually countability axioms. So this is for last session. So there we have seen the importance of first countability axioms. Okay. So spaces first counter means they satisfy all the sequential criteria as good as metric space. So first counter space is near to metric space, but of course not fully. So that's how much it is differ from being a metric space. That's coming the second counter space. So that is the thing. Okay. So now the second thing comes is the separation axiom, which will start today. But before going to separation axiom, so there are some interesting counter examples of the countability axiom, which we will see today. So, for example, product of Lindelof space, product of Spadal space, or Spadal not, those type of things. Okay, so it's basically counter type of thing. Okay, so there is nothing really new about it, except from some explaining the counter example. Okay, okay. So first, today we will see first one of the very interesting example is that. So we have seen that Lindelof space. Lindelof space means what? Lindelof space means any compact space means any open cover has a finite subcover. And Lindelof space means any open cover has a countable subcover. So that is the thing. So now product, we have seen the product of two compact is compact, but in the Lindelof situation, product of Lindelof space may not be Lindelof. So that's what we are going to see the first example. So let me write it down. First statement that one product of Lindelof space is not Lindelof. There is a so so for this we need to choose a product space, right? So now our lower limit topology is the Lindelof. Okay, the proof will be seen later. So proof later. But we have seen the step in the previous section. So R is lower limit to Lindelof. But RL cross is not Lindelof. That is it. So for that, for this, what want, we can do the following. We can choose an open cover. Sorry, huh? Yeah, okay. So for this, we can choose an open cover of RL cross RL, and we then show that it does not admit a countable subcover at any cost. By the way, this RL cross RL is known as it is known as Sorgen Frame. It is popularly known like this. Anyway, there is nothing interesting about it. Wait, kind of 1 minute. Well, what we can do is the following, namely, um, so we will try to consider open cover which does not admit a counter. Okay. So for this, we can. So there is a following trick which we need to use. Okay. So, so suppose this is RL plus RL. And now consider the following line. So what is this line? This line is x comma minus x. Call this line L. Okay. So first of so clear. I mean clearly L is closed. Question is why? Closed in where? Closed in Rn. So look, it's not a matrix, it's a topological space. For matrix, it was directly easy to prove that that L is closed. But in metric, in topological space, what we need to do? We need to prove by checking opens and closed. But comes the advantage of here comes the advantage of first countable space. So look, we have seen that Rl is the first count. So is RL. So now since the space is corresponding space, so any subset closed or not, for this what we can do, we can choose a sequence, and if we and the element, and I mean we can take the sequential criteria of showing some set is closed or not. That is what? That is if a set capital is closed if and only for any x belongs to there is a sequence xn in x such that xn goes to x as xn revealed or not. Okay. So this is what we are trying to show. So now what? So now suppose xn yn be a sequence in there such that xn comma yn goes to x comma y. We want to show that x comma y belongs to it is equivalent to showing, so that is equivalent to showing that y equal to minus x, right? So how to prove it? So first of all, so x minus xn is equal to y, right? And xn goes to and this is what? Since first quoted, so pi 1 is the projection math is what? Xn goes to x, y goes to y. Okay, correct? So this implies what? This implies minus yn goes to minus y. Sorry, minus yn goes to x. So this implies yn goes to minus x. So this implies y equal to minus x due to Hausdorff test. Roughness is y given. So this tells what? So this L is closed. So let me repeat it again. Why the set is closed? So look, in order to show something is closed here, we can't use matrix because topological space does not have in general those kind of sequential criteria in general. But since the space is first countable, so we have the advantage of using first countability actions, especially sequential criteria of a set to be first closed. That is if we take any sequence xn in capital A such that xn goes to x, then the limit point will belongs to xn capital A. So here what we have done, here we do xn comma yn in L such that xn comma y belongs to x comma y. So now the rest of our follow. So what we have seen? So we have seen that L is closed. Okay. So L is closed with what? So this tells what? This tells that RL2 minus L is open. And this tells so RL2 minus L is correct. Now Now this is L. Okay. Now for suppose we are choosing some point x comma y outside L. Okay, so leave it. So RL minus L is open. Okay, so this is this serves an open set of some following open of which are going to construct. Okay. So now choose some point here x comma y. Now we want to cover this point by what is that point? So this is one thing and this is one, correct? So that suppose this is epsilon one and this is y plus epsilon. So state can be written as x comma x plus epsilon one comma y plus epsilon. This is open in Rn. Okay. So for each of these points, we can choose this open cover, correct? And this set contain x comma y. So this set x comma x plus epsilon one cross y comma y plus epsilon two union. We can find epsilon equals to this zero, x and y belongs to L. Union this L. This whole thing is an open cover of Rn. Correct. Now, point is simple. Now we are going to prove. Now we shall see that it does not admit counters of word. Okay. So now we are sure it does not count as words. How do we do? So suppose, so for this we are going to I mean, so so argument is simple. So suppose if this thing admits a countable subpower, okay. So suppose it admits countable subpower, then L will be then the line L will be subset of countable union of countable union x comma x plus epsilon cross y comma y plus epsilon. But observe what L this line intersects this x comma x plus epsilon cross y comma y epsilon in exactly. So L but L uncountable. So L cannot be covered by countable things. That's the point. Okay. So L cannot be covered by countable subcollection. So So let me re-explain our approach. So okay. So initio. So what we are trying to show, we are trying to show that every open cover, uh, we're trying to show that this open cover does not have an account. So yeah. So the product links is not included. This is what we want to show. So for that we first took the ritual similar space and now we are proving that it does not now we are going to show that this the surgery plane is not lethal. Okay, so for this what we want to do, we need to find an open cover which does not have a countable subset, correct? So as an open cover what we have chosen. So as an open cover with this, so here the trigger as an open cover we need to choose something which we are doing it. So for that first we took the line y equal to minus x. This. So this is the line y equal to minus x. So now first target is that this line is closed in Rn. So this is the first thing. So after proof, so for, in order to prove this, what we have done, we have taken this, I mean so then space the first countable, so we can use the battery in order to prove that this line is closed. Okay, so that's not the main thing. The main thing is that after main thing comes after that. So this line is closed. So complement of this line is open. Okay. So that's good. So this complement of line. So now this thing consists serves as an operation of the open cover which is going constant. Now only the points on the line remains serves the rest. So for each point we can choose an open cover like this. So now for each of this point we are choosing some open neighborhoods like this and this contain this union the capital open cover R. Now claiming that this open cover does not have any countable sum because it has countable sum cover. This line is subset of the countable collection of this set of four. But if we look at the diagram, this type of point intersect this type of intersect this line capital in exactly one point. So that's why but capital contains uncounted many points. So that's why this collection, this countable collection cannot cover this capital. So that's why that's R into is not. So that is the argument. Are you able to understand? I shall wait for 2-3 minutes. Let me know, or else we shall go next thing. I shall wait for 2-3 minutes, or else we shall move for the next thing. Please take your time and let me know. Okay, it seems that this argument is quite clear. So well, so now let's move to next useful things. So well, so now let's go for some exercises. So the first question, let f x to y be equal. Show that if x is lambda, then fx. So this is the question. So let me see. It's very kind of message over chat box. But yeah. So question is, suppose f is a map from x to a continuous, show that f is linear, then f x. So if x is linear, then f x is linear. So how to prove this? Or what are the ways to proving this? Or think about it. Let me know. So basically, I mean, so you need to the so whatever, so the same way as proving as for continuous for compact space images compact. Okay. So the same argument will work, but you need to make the argument wrong. Okay. So that is the thing only. So think about it, how to make the same argument. In compact case, there is a finite set, and here is a countable value. So that's all. And there is nothing really complicated about it. So okay. So how to prove? So basically there is nothing complicated. Okay. So fx in the left. Okay. So let u be an open cover of fx. Okay. That is fx has to the union of u alpha. U alpha and open and y. Yeah, u alpha open and y. So this implies what? This implies x equal to union of alpha if inverse alpha. Now each of these are open since if continuous. Okay. So there is nothing complicated now here. Now since what? Since x length of, so x as countable sub. So what? So x equal to union of alpha I, sorry, union of I is equal to 1 to infinity if inverse u alpha I. So this implies f of x subset of union of 1 to infinity u alpha I. So this implies f x is lambda out. So that is the okay. So there is really nothing much very complicated here. So are you able to understand argument? So what we have done, we choose an open cover, we choose an open set, sorry, open covered around y, and we are simply taking open cover of a x inverse image that's open. Now we take the envelope so that inverse image so that inverse image collection is counted with covers cover. So that is okay. So that's it. So think about, let me know, do you have any questions or else we shall move forward next week. So next question. If X has countable dense subset and if f of x be continuous, then show f(x) satisfies this set. So how to do it? So it is actually technically same as the previous one. Just think about it, how to proceed, okay? Or else I shall solve it for you. I'm giving for 2 3 minutes. Think about it. Let me so let's so so that is what we want to show that f(x) as a countable. How to do it? Let G be the, so since capital X is countable, then so let G be the is capital C. Well, as for that, Well, okay. So let's sorry for the inconvenience. So that is the closure equal to. I'm claiming that f of t is countable is subset of f of x. So this is my claim. Okay. How to prove it? So now point is that f of the closure subset of f of the full closure by continuity. So these are criteria for continuity. Now point is that f of the closure is what? That is f of x. Correct. So this is the spot. F of x subset of f of the closure. So this implies what? F of the distance f of x. That is argument. So that is it. And there is really okay, that's all. So let me know. So do you have any question? For the next as a look. So what we have done, we have started the given countable test with capital X. It is countable. F of t is already given. We need to prove the denseness, right? So in order to prove denseness, what we have to f of t is the countable test, and for this we have used a special criteria of the continuity. That's all. So this will be the ability test. So now think about it and let me know whether this argument is clear to you or not. So I hope this much is clear. Well, so now let's next question. So next question is as follows. Question is let f of x to y be contains open map. Show that if x is first countable or second, then fx satisfies the same. So just for the previous problem, this is also similar type of problem, but it's always good to solve the problem. So this is the problem session. So anyway, think about it and let me know whether you're able to solve it or not, or else I shall really learn it. Okay. So well, so the same kind of argument. Okay, I correct. So well, so I will be any either person. Okay. So let X person. So limit X is so let capital X is countable basis for its topology. So now, so now, so now, obviously, as you mentioned, what is the claim? The claim will f of capital B will be countable basis for topology for of the correct. First of all, why this thing makes sense? It makes sense. So now, why this basis? What makes sense? This makes sense because it's open. Because it makes sense. Because say they so that's why it makes sense. And there is nothing. So now, we want to prove the result. So for this, what we do? We choose an element y belongs to fx and open set. Okay. So this is the x belongs to f inverse. Okay. Now since capital B is obviously right, so then there exists a bx belongs to beta such that x belongs to bx of f inverse. Correct. So this is y belongs to f of bx of. So this is what? So this is why this is an element belongs to f. So that is what. So that's f of this and counter based on topology. So this is what we are trying to do. So that's why. So that's why. Now think about it. So basically we have done what we took the given we took the given open set of capital X. So basically capital basis capital X which we are working with capital. And there we are taking that if we take the f of those elements that will open because f is open. Then we are choosing that over a kernel satisfied condition. So that is something. So thank you. Let me know if you have any question or else we should for the next problem. So let's move to the next one. What's that? So let's say well. So next question is this So the next question is as follows, namely, show that if x,
Hello, sir.
yeah, can you start?
In that text book, I have seen product of Lindelof is not Lindelof. Can you explain the argument?
Well, so yeah, I have already explained it, but let me re-explain it again for you. Okay. Yeah, it's a quite tricky argument, I understand. So yeah, so in order to prove this, I mean, in order to provide a counter example, we have chosen a space which is in love. Okay, so the space is R with lower limit topology, and we are going to prove that RL2, that is RL cross RL, is not in love, and namely this RL2 is known as surgery. Okay, now we want to prove that this surgeon free plane is not linear. So for that, what we need to do, we need to make an open cover which does not have a finite subcover, right? So first of all, we need to make an open cover. Okay. So the trick comes here. We are not going to make open cover directly. We are choosing the line y equal to minus x in the surgeon free plane. First, we're claiming that the surgeon free plane is a closed set. How? Look, we directly by method of matrix we cannot do it because topology is, but since observe that the lower limit topology first countable space is product also first countable space. Okay, so that's why we can use the sequential criteria of a space being closed, a subspace being closed. Okay, so by that way we prove that the y line y minus is a closed set. Okay, now now what we're doing, we are now so the line L equal to L closed set. Now now, if you look in the picture, so only the line, since L is closed, so RL minus L is open. Okay. So now only the the points in L remains left for covering by some opens. Correct. So now choose any point from L. So now if we're choosing the point L and so call the point x comma y, then the open set third bracket x comma x plus epsilon and for across y comma y epsilon 2, those consist of what? So this thing is an open cover of capital X. Okay. Now the point is that we can check this type of open sets for each of the point in L. Now we are choosing the line union those two opens. Now claiming this is an open cover of real RL2, that's okay, but we are going to prove that this does not have a countable subcover. Why? Because if this admit a countable subcover, then the line L will be subset of the countable union of the elements of this type of form. But that is not the case because this line L intersects only elements of this form, this x comma x plus epsilon y comma x exactly in one point, but the line L has incountable many points. So this line L cannot be covered by countable sub collection of that open cover. So that's why the RL2 is not Lindelof. Okay, so that's the argument. Are you able to understand? Are you able to understand? Let me know.
Yeah, yeah, I can.
Okay.
So another thing,
Yeah.
R with K topology is house drop or not? Can you repeat? the-
Well, so I think that has been done by certain class. So well, so till now we have not reached up to that separation axiom. So keep patience. After few minutes or possibly after reaching the separation axiom, we can discuss the problem. Okay. Till now we have not reached the separation axiom. So that's why right now we are not able to describe this thing. We are right now we are not in the position to able to describe it. So today we shall reach the separation axiom and then we will discuss. Okay. I hope that's fine for you. Do you have any more questions?
Yeah.
Yeah. So So yeah, so the question that we are trying to solve right now is the following. Hmm. So yeah, so the question is if x has a countable dense subset, countable dense subset, then every collection, sorry, of disjoint open sets in X X a countable dense subset, then every collection of disjoint open sets in X. Another question. Think about it. We need to use countable dense and we need to say disjoint open sets in X countable. So suppose the uncountable and try to show that dense set cannot be countable. That is the way we create information. So so let me so let U be a collection of joint. Now since D is dense, so call D with a dense. It's dense X, so U intersection D will be non-empty for all collections. So that is what? That is each U, so that is each open set U contains at least one element of. So this collection U has to be countable. Why? Otherwise, D will be countable. So otherwise, D will be uncountable. So that is it. So are you able to understand the argument? Argument is really easy. So, then U be an collection of distant open X. Now since U is 10, so U intersection D is 1. Okay. So now since this open curve, so now since U intersection D is not empty, each U will contain at least one element of two. So U be an U has an countable. So I mean that the collection U is countable, otherwise G will be uncountable. So that is the case. So that is the thing. So yeah. So now the next thing which we are going to the next we are going to well. So let's start with things known as separation issues. So let's start with separation issue. So so basically, so separation axiom, as the name suggests, it is a property of some space by which we can ensure that suppose we have given 2 points, is it possible to separate those 2 points by some open set? Suppose we have a point and a closed set, is it possible to that point and a closed set separate by some open set? This type of problem can be answered by using separation axiom. So so there are basically three things. First one is Hausdorff, second one is regularity, third one is normality. Okay. So these are total three things which we are doing. So now, so of course, so there is no need to out of this. So let's start with regularity. So for this space, the assumption singleton set is closed. Okay. So regular. A space is said to be regular. A space X is said to be regular if for each point x belongs to x and open set u containing x with x does not belong to u. Sorry, it's a closed set. Okay, so it's not open set. It's always closed set. There exists open sets. So if this happens, then the space is said. So that is we have a space, and if for each x belongs to you choose any point and you need any overall set not containing that point, so it should be closed set. So it should not contain points. That opens the point with x belongs to and f belongs to. F is something that is explanation. So that and so now and regularity definition is almost same, but slightly different. So normally everything same. So closed sets f1 f2 subsets of x which are disjoints with f1 intersection f2. There exist open sets u1 u2 with f1 subset of u1 and f2 subset of u2 such that u1 is intersection u2 is there. So that is the normality. Okay? So there is really nothing different. Okay, so there is also that is. So for regularity, what will be for regularity? The point will be there and closer will be point as closer, then there is open sets so that they are intersection. And for normal you have f1 f2 with the intersection empty. There is open set e1 e2 contain that close that so the e1 is. So that is the thing definitely. That is the thing between regular and normal. So till now let me know do you have any good definition or so do you have any question on intersection. So so there is a thing. Okay. So there is really nothing to say. Well, so now first observation is observation. So normality implies regularity implies housewife. So what about this? So of course. So if you look at the definition normality, well, so if you look at the definition normality, what is it? It was telling that if you take any closed disjoint sets, they can be separated by disjoint over. So now we have seen the singletons closed. So since singleton closed, so singleton X is our closed set. Now if we take any F not containing X, there is no open set U1, 2, and U1 subset F, U2 contains F, such that U1 set. So that's a so it's and by putting A is equal to similar to Y, so that is the thing. So it is so normal space implies regular space house space. So that is it. So now the next fact, well, well, but the as expected converse one. So so now the question which Mustaq asked around ago, now it's coming. Now the point is that so for that first we need to space in the house of multiple. So first example is the alkene policy is house of but not regular. Okay. So well now. So these are suitable house of multiple. So how to put this? So so first of all is that R with K topology is house term. Why? As it is finite that R with usual topology, and it R with usual topology is Hausdorff. So R with K topology is also Hausdorff. And there is really nothing much to say. Now question is, R K topology is not regular. Question is why? So in order to prove that something is not regular, what we need to actually know? Well, so you guys are back in 2 minutes. Well, so arc is not regular. How? So, so first of all, recall that the basis of Rk are the opens of the form AB and AB minus capital Okay, here this capital K is the element of the sequence 1 by n. Okay. Now, so clearly this capital K is closed in R form. And of course, 0 does not belong to capital. Let there exist open sets U and V containing 0 and capital K respectively. Choose a base element containing 0 and line. So definitely it must be a form open every minus as each basis element of the form open AB containing 0 will intersect K due to what? Due to Archimedean property. So basically now so this is our okay, this is suppose A, suppose B, it is our point 0, it is C, it is D, it is Z, it is 1y. Okay. Now choose n large such that 1 by n belongs to open and find take an basis element about 1 by n continuity. So it must be basis element of the form C. Now, so it must of so now choose one. Choose the Z with Z letter one and set it maxi comma 1. So Z belongs to 4. They are not short. So that is so please go through the explanation. I shall again please go please go through this. So now let me re-explain this. So basically, our target is to show that R with K topology is house drop quadratic. It says RK is house drop. There is nothing to discuss about that. Now RK is regular or not. RK is not regular. Why? So first, before going to that, so let's recall how the open RK looks like. So the uh, so basis of RK is open AB and open AB minus K, and K is closed in RK, and 0 does not belong to K. Obviously. So now we are going to show that the point 0 and the screw set capital K, these are not possible. It cannot be so these two things cannot be disjoined by means of opens. Okay. So suppose yes, so we are now choosing an base element 0 lying in Q. So definitely must be the form open minus Q. Why? Because 0 does not use, I mean, 0 does not use, so any open set containing any open set of the form open AB contains 0 bases. So that's not the case. Now choosing n large enough so that 1 by plus open AB. And now look at the diagram left side. So we are choosing S as the 1 belongs to open and take a basis element around 1 by continuity. So it must be of the form open comma C. Now choose Z with Z as a 1 by L. So then Z gets the maximum C comma 1 by plus 1. So Z belongs to U and B, so they are not disjoint. So that is so that's a contradiction. So it is not regular. So the Musta definition of RK is house of water regular has been solved. Let me know whether are you able to understand.
Yeah, I understood.
Uh, do you have any more questions from Sir's session? So now the thing which comes, the question comes to the following: the space R. So R is lower level topologist. Now, how to do it? First think about it. First think about it. Let me know if you are not able to solve. I shall do it. Okay, so let's wait for it. So what we so we, for in order to do this, we need to choose to close the joint, right? So let A and B close this and so they are destroyed. So for each A belongs to a basis element, A comma X A not or each belongs to be two basis element B comma X A not intersect. Now define the open U A comma X A belongs to A and open B union B comma X A is disjoint sets. So now what we are going to show that this set is so now so obviously U contains capital A and of course B contains capital. Now we are to show that this is empty. So suppose let P belongs to the section. This is what P belongs to A naught X A naught intersection B naught X. So A naught less than T less than X naught. B naught less than equal to T less than X. Okay. So these bring us what? Either A naught less than equal to B naught or B naught less than equal to A naught. So this gives what? This gives that A naught comma X A naught intersection B empty not empty. Or these things we got B naught comma X B naught intersection A naught. So that is the contradiction. So let me repeat. So so we chose two open set to close sets A and B are L disjoint, and we took a point A capital A, we choose base element A comma X intersection B empty and B comma B intersection. Now we are choosing U to be sorry. Now we're choosing U to be union of X and B. Which over the universe. Now obviously U belongs to capital, B belongs to capital. So there is nothing. Now suppose now we need to show the unit system. So suppose T belongs to this. So this plus one. This T belongs to A naught comma X A naught and B naught by X. But this is what A naught less than equal to T less than X naught, B naught less than X. So these implies A naught less than equal to B not or be not listening to him. So that's giving a contradiction. So that's giving what? That's giving that be not connection or intersection or be not connection or intersection. So that is a well. So Mustaq, that's all for today. Today it's only few seconds left. So if you have any doubt, you can ask me right now, or else we can stop here or start from the next session. Um, from next day, we shall first start the problems. If you have any doubts from the student session, you can ask the problem in the next session. Also, you can drop an email to me. I shall get back to you by reply, or I shall solve in the next session. Okay. So, well, so let's stop here. We shall meet in the next, say next week, Friday, 7 to 9. Yeah. Thank you. I'm leaving the call.